across the World Wide Web, on your mobile devices, on social media platforms. This is Jambo Radio! www.jamboradio.co.uk. We are multilingual. We are conversational in the languages you best understand. We are Jambo Radio! Jambo Radio, inspiring transformation.
This is the Science Show with Dr. Dada. It's just so nice, you cannot do without. This is the Science Show with Dr. Dada. It's just so nice, you cannot do without.
Hello, and welcome to the Science Show with Dr. Dada on Jambo Radio Scotland, broadcasting live from the city of Glasgow. As usual, we'll be exploring the frontiers of science. And as you've probably noted, today's topic is very, very exciting. It's what's on the dark side of the universe. Dun, dun, dun. That sounds a bit scary, a bit spooky. I'm sure you'll be properly spooked today because this is one of the most exciting aspects of physics, of science, in fact. Today's guest is Professor Deepak. He's at the forefront of one of science's most exciting mysteries, and that is dark matter. And although we know that it exists, from the way that it bends light in the cosmos and the way that it shapes galaxies and so on, scientists still haven't seen this enigmatic substance directly or pinned down what it's made of. So for years, researchers have looked at dark matter and looked for what it's made up of, trying to understand it. And they've done so as a type of invisible particle called a WIMP, or weakly interacting massive particle. But after countless searches, nothing has shown up. But Professor Carr believes it's time to think differently. He's now exploring new theories that suggest dark matter could interact in surprising ways, even creating hidden jets of particles that are incredibly hard to detect. So today, join us as Professor Carr breaks down the new approaches of finding dark matter and explains what these elusive clues might reveal about the universe. Well, I'm so delighted to welcome you to the show today, Professor Deepak Carr.
Thank you. Thank you for having me. It's a pleasure.
Yes, it is. The pleasure is ours indeed. We're going to get to know you a little bit more. But first, we're going to summarize our first highlight, science news highlight for today. A little bit about Professor Carr. So Professor Carr is a professor of physics at the University of Wits.
We call it Witwatersrand.
Witwatersrand.
Right.
Yes. In Johannesburg, South Africa. And he's a dark matter researcher and he's part of the Atlas collaboration. You probably heard of that. It's a very famous collaboration. And we're going to hear more about that from Professor Carr himself. And so when it comes to our first news highlight for the week, it's not about dark matter, but it's something about matter. So scientists have discovered a new method for creating a very heavy element called livermorium. So livermorium is a super heavy element, as they call it. Now, this innovative technique could pave the way for the production of element 120. Perhaps, if you're familiar with the periodic table, there are certain elements that we don't know if it's possible to have them. It's possible if, for them to exist in a stable form. So element 120, it seems there's now some indication that it might be possible to produce it. And if that happens to be the case, it would be the heaviest element ever discovered. So that is going to be some proper new physics if that turns out to be the case. Actually, this story is based on a paper published in Physical Review Letters. And as we know, it's one of the top journals when it comes to new physics, So Physical Review Letters published in 2024, just a few weeks ago. And the title is Toward the Discovery of New Elements, Production of Livermorium Z is equal to 116 with titanium 50. It's amazing. I suggest that you really have a look at it. It has a long list of authors. It's one of those huge collaborations, but for good reason. So we'll explore that just a little bit more. So when it comes to livermorium, it's as we said, a super heavy element. It has 116 protons, and it's created by smashing a beam of titanium ions into a target made up of plutonium. Now, the experiment wasn't just about making livermorium, but it's about what it means for the future of element discovery, which is what we discussed earlier. Now, if this goes ahead, it means it opens the door to creating even heavier elements, like element 120. Dada! And you might be wondering why scientists are so obsessed with making these exotic elements that barely exist for a moment, right? Well, it's not just about, being able to say, oh yes, now we've made element 120, or we made element this, element that. There's a theory in nuclear physics called island of stability. Now, this theory predicts that somewhere in the upper reaches of the periodic table, there are super heavy elements that are much more stable than their neighbors. Now, just imagine finding an island of calm in a stormy sea. That's what it feels like on the periodic table, if you find these kind of stable, heavy elements. Now, what these stable, super heavy elements would be can be compared to that analogy. Now, finding these stable elements would be a major scientific discovery. It would not only confirm our understanding of nuclear physics, that, in fact, you do have that, but also it could lead to new technologies and materials with unimaginable properties. Imagine discovering new material, exotic materials, and think of all the amazing technologies and doors that they could open. So this is really interesting stuff. As I said, it's out in PRL. Okay, now with that out of the way, we're going to have a quick chat with Professor Deepak to get to know you a little bit better. So perhaps you could start with your background. I know at the moment you are in South Africa. At the moment you are in Glasgow.
Right.
Could you tell us about your journey and from where you were born,
Right.
and how that took you to South Africa, maybe through Glasgow, but now you're in Glasgow. So what's going on there?
Right. I probably have a very interesting trajectory in terms of my scientific career. So I was actually born in US,
Ooh.
but I don't really have a lot of memories of that because I only lived there for like 4.5 months.
Wow.
And funnily enough, my dad he's a physicist. He was a postdoc at that point when I was born. And then when I was like 4.5 months old, they moved to UK. But they stayed there for like a year. My dad was working in Dartbury Laboratory, which is close to Liverpool, I believe. But I still don't have any memories of that. And then I went back to India. My parents went back to India. I grew up in a small town called Siliguri, which is in the eastern part of India. But because my dad was a physicist, I heard a lot about physics in my formative years. My uncle is also a physicist, so physics kind of ran in the family. My dad would bring like books from the library because he was in the university, and I read like all those pop science books and get so excited about everything physics. So that's how kind of my interest grew, and then I took physics in the university. Of course, I had a lecturer who was super inspiring. I think many of had that experience. So yeah. And then I came back to US for my PhD. I went to University of Florida, where I did my PhD in particle physics, and that's when I became a particle physics. But then I came back to Europe as a postdoc. I was in Germany for almost 3 years, and then I landed up in this lovely city of Glasgow in 2012. Wow. I was a postdoc here for 3 years. I enjoyed my time. I love Glasgow.
Amazing.
Yeah, yeah. And then we were looking for a job. I mean, academics, we also have to find a job. Even though we love physics, we love what we do.
Yeah.
And I was looking for jobs everywhere. I stumbled on this position in South Africa, and I was like, I'll just apply because I need a job. And I got the job. I'm like, okay, I've not really been to South Africa, but let's see how it goes. And 8.5 years down the line, I'm still there. I'm not still there now. So after a few years in academia, you get like a sabbatical year where you can actually focus on your research, explore new things, explore collaborations. And I was like, what do I want to spend this sabbatical year? The answer was Glasgow, my favorite city. I was lucky to get a Royal Society fellowship who funded my stay. So a huge thanks, huge shout out to Royal Society for making this happen. But yeah, I'm so happy to be back in Glasgow.
That's wonderful. Wonderful trajectory. So I remember seeing somewhere, I can't remember if it was your LinkedIn profile, about the number of countries you've been to. Was that you?
That's definitely me. So we all have like crazy hobbies. Not all, but many people do. My crazy hobby, and I know this is a very expensive hobby, to go to as many new countries as one can. I mean, it sounds as crazy as it is. As of now, I have been to 119 countries from the UN list. Yeah, and I mean, that keeps me going. When I'm not doing science, that's probably what I do.
That's a great hobby, to be honest. It's a really, really nice hobby. You get to be exposed to many new cultures.
Absolutely.
And maybe, while you're visiting a city, a country, maybe visit their physics, like in the universities, and get more collaborations going on as well, perhaps.
Yeah, that's definitely a part of it. I mean, I remember quite a few years back, I was in Cuba. Now, as I just told you, I was born in US, so I have a US passport, which makes going to Cuba quite hard. I mean, they don't like it. However, there is an exception that if you visit a physics department, then your trip is for academic purpose. So I kind of exploited that loophole.
Okay.
I visited the physics department in the University of Havana. I met some lovely people there, gave a seminar, talked about physics. It was a day. I mean, it was lovely to see like a physics department, as you just said, in another country, in a very different country. So yeah, that happens. I went to Pakistan a couple of years back. Again, because I work in Atlas, a big collaboration with LHC. As you can see, I mean, we work with a lot of people. So there are some Pakistani colleagues. They're like, oh, you are visiting our lovely country. Why don't you visit the department?
Exactly.
And again, a big shout out to them. The day I visited the department, they took care of me. I mean, I had a seminar in the morning. I mean, they took me to a lovely place for lunch. And then they essentially guided me to see Lahore, where I was. And seeing a new city with a local, nothing beats it.
True. I agree with that. Fantastic. That's wonderful. So, yeah, it will be interesting to hear more from you about, dark matter and all its dark secrets, and the stuff that we don't know yet, the stuff we know so far. And so, South Africa then, what's it like there? Obviously, South Africa is very advanced, in very many aspects. But what's science like in South Africa, in your experience?
I mean, I have been pleasantly surprised. I'm not going to lie, because when I moved there, I was worried that it's a developing country. And like many other developing countries, I mean, I grew up in India, so I know we have a lot of problems, which is, But moving to South Africa, I saw, sure, there are problems. But the government was very invested in science. So, as Dr. Dada said, I'm part of the Atlas collaboration. Now, what we probably don't know is to become part of the CERN experiments, one has to essentially invest in membership. So you have to pay a membership fee for every member, which is not an insignificant amount. It's like 10,000 Swiss francs, so probably 8,000 pounds or something.
Is that for a year?
For a year for every scientist, every person with a PhD.
I see.
And that's quite expensive. If you look at the whole continent of Africa, there are only like few countries who have collaborations with CERN. South Africa is probably the largest. Morocco has that. And Egypt has that. And I believe Nigeria has joined recently. So there are like 4 countries who actually are able to invest this kind of resources for science, which is amazing.
It is indeed. Wow, that's an interesting thing to know about CERN and how to collaborate there. It's fantastic work, that's going on there. We're going to hear more about it after the music break. So our first music break, we're going to listen to a song that's suddenly become very popular for usual reasons. A post went viral and everybody's suddenly talking about Vivienne this, Vivienne that. Anyway, this is the original song from back in the day, and it's by Prince Aimé. It's entitled Vivienne, and we'll be right back.
Papa, il doit être dans des gâteaux, le bas au bas des doigts là. Pendant la semaine, je lui donne mon argent, le lendemain revient encore. C'est pas dans tout la somme dont tu m'avais remis. Je devais de l'argent à une camarade, elle a réclamé, je lui ai remis. Je t'en prie Doudou, encore un peu d'argent, je sens, je donne. Si Didier voit honnêtement sur sa soeur ou sur sa camarade, Didier viendra me dire, regarde le vêtement là sur ma soeur, ce sont des bouts qui achètent. Si tu aimerais que je vienne chez toi, il faut d'abord acheter le mien. Comme celui-là, si c'est le vêtement de 50 000, j'achèterai. Si c'est le vêtement de 100 000, j'achèterai. Et comme les vêtements des prostituées ne coûtent jamais moins cher.
Yes, that was Vivienne by Prince Aimé. Very interesting story about Prince Aimé. He's actually blind, and the song is a story about a certain Vivienne who took his money and ran away, and you know the rest of it. So it's just interesting to see that about a decade after he releases the song, or maybe even longer, now the song is doing really well, and I'm so happy for him. But anyway, this is the Science Show with Dr. Dada on Jambo Radio Scotland, broadcasting live from the city of Glasgow. And I'd like to shout out to our sponsor. I'll take this opportunity to do that, and that's our past sponsor, IOP Scotland. We'd like to shout out to the University of Glasgow, where I work, and where Professor Deepak is doing his sabbatical and his fellowship at the moment. And we'd also like to shout out to the Royal Society, of course, for sponsoring the fellowship that Professor Carr is on. And for our show, we welcome you to join in the discussion. If you'd like to chip in or ask us any questions, or just share a thought or two, you can call 0141 530 2787. 0141 530 2787. So feel free to do that if you'd like to. And also, we're broadcasting live on DAB, so you can listen to us if you have a digital radio and you're in Glasgow or Edinburgh or surrounding towns. And you can also listen and watch us live on YouTube, so on our YouTube channel, Jambo Radio Scotland YouTube channel. And episodes are also uploaded to our YouTube channel, and you can sort of catch up with past episodes of the show that way. So, very good. So coming to our second highlight, news highlight on the show this week. So one of the other headlines that caught my attention was about something related to what we're going to talk about today, which is dark energy. So the headline said, early dark energy could resolve cosmology's two biggest puzzles. So, it's about the fact that physicists propose that a mysterious force known as early dark energy could solve two of the biggest puzzles in cosmology and fill in major gaps in our understanding of how the universe evolved, the early universe evolved. So we're not going to go too deep into that story, but perhaps we could just explore a little bit what dark energy is, and that will lead us nicely into our discussion about dark matter. And of course, we have an expert in the studio who's going to guide us in all of that. So could you perhaps enlighten us a little bit, first of all, about this headline? What is dark energy?
I wish I could tell you we know, but we don't. No one does. Just like dark matter, we don't know. Like your earlier headline, where I won't say it's easy, but in certain areas, discoveries, new physics is easier. I won't say easier. That's probably but it's comparatively easier to find new physics. Whereas in my field, particle physics, it's so hard. So dark energy is this mysterious energy which kind of accelerates the expansion of the universe. That's all we know. That's pretty much all we know. So the universe after Big Bang is expanding at a rate, and we have measured that. Scientists have measured that, and they realized that the rate of expansion is actually increasing, and there has to be an extra energy kind of pushing that expansion. That's dark energy. That's all we know. That's pretty much all we know.
That's interesting. Do you have any insight into why it's called dark energy? Is it just because it's not visible?
I would say that's pretty much it. I mean, it's not something we could sense or find in any other ways, except that it has this mysterious effect. And it accounts for like 68% of our universe, which is crazy. We don't understand 68% of our universe, which is dark energy, and further 25%, which is dark matter, which I believe we're going to talk about.
Yes.
So essentially, we are sitting here and looking at everything around us, and that's the visible matter, the matter which emits light, reflects light. That's just 5%. How crazy is that?
Just a small fraction of what's out there. Wow. That's mind-blowing, isn't it?
It is.
It is absolutely mind-blowing. And it leaves, talking about new physics, it leaves a lot of things to be discovered. You don't know what the implications would be. What are we going to find next, that will throw light, as it were, on dark energy and dark matter.
Right.
So anyway, that story, that highlight that we mentioned is published in the monthly notices of the Royal Astronomical Society, and it was also published 2024, very recent, from just a couple of weeks ago. And the title is Early Galaxies and Early Dark Energy, a unified solution to the Hubble tension and puzzles of massive bright galaxies, revealed by JWST. So yes, please check that out. You'll get all the juicy information and details in there. So now let's talk a little bit more about the topic that we're looking at today, which is very exciting indeed. When it comes to dark matter. So what's on the dark side of the universe? So that's a little bit of a play on words, isn't it? It reminds you of, the Jedis on the dark side and the, all that stuff. But it's interesting to contemplate, to think that the universe has a dark side. And of course, it's called the dark side because we don't detect any light from it. It's not visible, if you like, if you want to use that terminology. But there are other ways in which it manifests itself, like the effects are felt in a way. So it sounds mysterious. So, Professor Carr, could you maybe start by telling us what dark matter is? And I'm afraid I know what the answer is going to be, but at least you know a bit more about it than the rest of us. So,
I would like to believe that. Thanks for that question. But yeah, we don't actually know. No one knows. But what we know is something exists. Something is responsible for the motion of galaxies and keeping them together. Otherwise, I mean, except this extra mass, extra hidden mass pulling galaxies, they would split apart. And I mean, there is probably dark matter passing through this room right now. We just don't know what they are. So there are many different ways we physicists try to search for it because we don't know what it is. So we have to essentially explore all the options we can think of and maybe beyond.
That's absolutely mind-boggling, isn't it? Dark matter. It could be passing through. And, the other day I saw a headline as well, not long ago, that scientists think, there may be black holes that are tiny, so tiny that they might pass through your brain and you wouldn't even know.
Right.
But they'll maybe leave a hole behind. So a hole so tiny that, it's not such a big deal. And that kind of leads me to the next question, which is, we know about black holes. They're a bit more well understood, right? These black holes. Now, I understand that in the cosmos, one of the ways that you detect or you know the presence of dark matter is the fact that it bends light, much like a black hole does, right? So how do we know, just for the benefit of those of us who are not specialists, what's the distinction between dark matter and black holes? How do we know these things are not actually some form of black holes?
That's a hard question. And I have to admit that I'm not an expert on astrophysics or cosmology, but my understanding would be that black holes, we can still kind of understand their presence based on their attraction on other objects. And I think that by itself doesn't resolve the whole missing mass. So we know that there has to be more, and probably the way they bend light would be different because dark matter would have a different force field or whatever. I'm not going to go into too much details because I don't want to say something wrong, but that's probably what it is. I mean, the effect would be different.
Yes, I see. And I know, the black holes, we can observe them gobble up things like stars and other objects. And also, they have this glow around them, don't they? With, the event horizon, you can see the glow because of the hot gas around the event horizon emitting light. So maybe that's also another aspect to it. But yeah, it's just something I'm like, how are you sure these dark matter, these objects are not some form of manifestation of black holes, and perhaps maybe from the way they bend light as well, some things could be said about the density maybe or something like that. But anyway, it's one of those very interesting things. And could you tell us a little bit about some of the facilities, the sort of research equipment that are used to, do the science? So for example, the LHC, what's the LHC? What happens there and what's it about?
I'm glad you asked that because that's what I spend my research time on. So LHC stands for Large Hadron Collider, which sounds a mouthful, but it's essentially we are colliding protons. We are accelerating protons to essentially speed of light, and we are colliding them against each other in a ring which is 27 kilometers of circumference.
Wow.
And when we collide protons, they break apart. They create a lot of new particles. We like to say that we essentially create a Big Bang-like condition for like an instant moment, and we try to kind of take a snapshot of what's coming out of the collision. Of course, nature is not kind, so most of the events that happens are kind of consistent with what we understand about nature, which is encapsulated in this theory called the Standard Model, which explains everything we know about elementary particles and the interactions. So most of the events are actually very Standard Model-like. We are looking at those rare events, looking for like needle in haystack in some way, something which is not conforming to standard model. That can be a dark matter, that can be a new particle. Some of the listeners might have heard about supersymmetry. All of these things, all of these fascinating new things which we are looking for at the Large Hadron Collider.
Wow, that's amazing. It's just very, very fascinating, isn't it? The other day we had Professor David Ireland on the show, and he was talking about quarks and the fact that quarks they stick so closely together that by the time you've had enough energy to split them apart, then you've had you have enough energy by means of E is equal to mc squared to generate more quarks, and they just form more protons or whatever. And it's just amazing. And the fact that you have the opportunity to at least do the science and check and at least attempt to study these particles and these forms of matter is just mind-blowing. But I think after the break we're going to talk a little bit more about the LHC and about dark matter. But for now, let's take another music break, and this time we're going to listen to another song from the Francophone part of Africa, and this song is entitled Ça va aller. Yes, that's the title, and it's by G7 and Impressions des Arts. And we'll be right back.
Mwana mutu wazabala matinwe, wazabala matinwe, wazabala matinwe.
le procureur.
Fantastic. Yeah, that was very, very nice, very bouncy song as well, indeed. So that was Ça va aller by G7 and Impressions des Arts. And this is the Science Show with Dr. Dada on Jambo Radio Scotland, broadcasting from the city of Glasgow. So, before we continue our talk about dark matter, I just wanted to mention another highlight from the news that caught my eye. And the title is Amateur Discovers the Largest Known Prime Number, and it's huge. Can you imagine the largest known prime number? You probably know about prime numbers. They're so strange in the sense that scientists, they've found it difficult, if not impossible, to find a pattern of these prime numbers. For example, you've got even numbers. There's a pattern, there's a formula for getting the next and the next, even number. Odd numbers are the same. But prime numbers, they just seem to pop up, randomly as you count higher in number. So it's very interesting that in the world of mathematics, recently they celebrated a pretty big win, and that's the discovery of this new prime number. And it's huge. You can imagine, it's a monster. And as the headline said, it's an amateur, you could say, who discovered it. So this was a former NVIDIA employee by the name of Luke Durant, and he only began contributing to the field, to the search of the next big prime number in October last year, although he had made a little more progress on that. So some people call it beginner's luck, if you like. But he made use of thousands of graphic processing unit servers spanning 24 data center regions in 17 different countries to run the software on his behalf. So you see, a lot went into discovering this new prime number. Perhaps you're asking, how large is the number? Are you ready for this? Now get this: 41 million digits. 41 million digits. Can you imagine that? That is just, in fact, so difficult, so big that it's difficult to wrap your head around that. Just imagine trying to write that on a piece of paper. It's going to take forever, isn't it? But let's back up for a second. What is a prime number? But simply put, it is a whole number greater than 1 and that can only be divided by 1 and itself. So think of numbers like 2, 3, 5, 7, 11, and so on. Now, that sounds easy, doesn't it? But here's where it gets interesting. Prime numbers, they're so important. They're incredibly important for a process called encryption. We've talked about that before on this show, if you remember. It's like putting a digital lock on your information to keep it from prying eyes. And it basically boils down to having two large prime numbers, multiplying them together, getting another large number. But if you start with the large number, it's really, really hard to find out which two prime numbers were multiplied to generate that huge number. So that's kind of breaking it down to a simple sort of form. But I guess that's a topic for another show. Maybe next time we'll talk about encryption. So you see, this is a very big sort of find for mathematicians. It gets them very excited. But anyway, let's get back to the topic for discussion this week. What's on the dark side of the universe? And that's talking about dark matter. Now, my next question to you, Professor Carr, is what would you say is the most exciting or unusual thing that you've discovered in your study of dark matter? Or maybe your research at the LHC so far?
That's a very interesting question. And before I go on that, I have to kind of add to that. We are talking about large numbers, like millions. We collide millions of protons every second at the Large Hadron Collider. Just to give a sense to our listeners.
Yes.
Coming back to that, now, as many of the listeners may be aware of, the last big discovery in the Large Hadron Collider discovered the Higgs boson, which created huge headlines, won a Nobel Prize for the discover, like the theoretical theorists who proposed that. And it's kind of funny because this was proposed in like 1960s, and then finally in 2012, after 50, 60 years, we found the Higgs boson. So that was the last big discovery. Now, in terms of, we haven't found new physics after that. But as I keep saying, when we perform our searches for dark matter, for new physics, and we do not find anything, that's also exciting. A null result actually tells us that we have looked at this parameter space, this mass of dark matter particles, this strength of dark matter particle interactions, hypothetical dark matter particles, of course.
Yes.
And we haven't seen them. So that kind of has incremental increase of knowledge, which hopefully would eventually lead us to a discovery. So even though we haven't found new physics, I mean, you would have known if we did.
Yes.
Dr. Dada would have covered it in great details. But we make incremental progress, and we look at data, and for like a day, it's like only me who has looked at that process, and we haven't found it, but I learned something. It's fascinating.
That's amazing. That's really, really amazing. Really nice place to be in terms of, it's a real privilege to be in your shoes in that respect. So now, when it comes to the LHC, you said something in your talk earlier today about the data that's available and the fact that perhaps in our lifetimes, there may be a limit, or maybe we may not get more data. Could you maybe expatiate on that a little bit? Because that sounds very interesting.
Sure. So LHC, the Large Hadron Collider we just talked about, is a unique facility in the sense that it's expensive, it's an engineering marvel, and it takes a lot of scientists and engineers, we shouldn't forget about engineers, to keep this thing running. It's a once-in-a-generational project. So, and it cannot be done by a single country. CERN has like so many member countries, not just from Europe, like most of the European countries are members and contributing, but there are countries from all over the world who are part of this endeavor. So it's a huge effort. No country can do it by themselves. So the current run, when we say run, we means like we are collecting data for months and years. It's going to go on till 2027 or so. Then we're going to stop and kind of refurbish our machinery, because we have the particle accelerator, which needs upgrade, and then we have the detectors, which are like cameras which take the snapshot of the collisions. Those need upgrades, those need maintenance. So we'll do that for a few years, and then we'll run for quite a number of years next decade. And that has been planned, that has been funded. So we are going to get that data, a lot of data to look for all new physics we want to look for. However, after that, nothing has been planned yet. And as I said, it takes decades to build a facility. It's so complex, so elaborate. So as of now, we don't really have anything concrete planned after the LHC closes after, let's say, 2040. I mean, hopefully something. I mean, people have been discussing quite a few options of future colliders. There is an active research going on, and there are lots of proposals, but nothing has been fixed as yet.
Wow. It feels a little bit sad and humbling to know that, sometimes we're so small, and, that data, even just the ability to collect data, may not be there. Think of some of the space missions, some star systems are so far away that, with the current state of things, it would be almost impossible to get there. If you're talking about something that's maybe thousands of light years, maybe even millions of light years away, how could you conceive of even getting there? Not to talk of getting there within the lifespan of a person. So it just humbles one, doesn't it, when you think about this? But what about you? How do you feel personally about reaching this sort of data limit as well? Does it change or affect in any way the way that you approach your research?
Not really, no. Because right now we are still developing techniques how to analyze this data better.
Okay.
We are actually using a lot of machine learning methods, which is a buzzword nowadays.
Yeah,
Everyone
absolutely.
is talking about machine learning and artificial intelligence. And we, particle physicists, we are the pioneers. We have been using these techniques for like decades. It's not known, but we have been using this to analyze our data because, as you correctly pointed out, we have such humongous amount of data. In fact, I'll just give an example to our listeners. Right now, the data we have, it's equivalent to if you run this podcast for like 20,000 years, non-stop, 24/7, and record that much data we have.
Wow, that
So we need innovative methods to look at data, and in my lifetime, I don't think I'll run out of ideas to analyze the data. So I'm not worried. I'm excited.
That's great. That's good. Okay, that's not so bad then. And yeah, could you just to break it down for those of us who are not so familiar with this whole idea of particle physics and dark matter? So, as we said in the introduction, there's this question about, theories about dark matter and where you come in. Could you maybe summarize that for us?
Awesome. Yeah, that's what I spent last few years of my life on. So, as Dr. Dada pointed out at the beginning, historically we have been looking at WIMPs, the weakly interacting massive particle, like a heavy dark matter particle, which accounts for its mass effects. And we haven't found it. That doesn't mean we have completely excluded that scenario, but that also means there are other ways we should look for it. Now, some theorists came up with an idea that dark matter, or we call this dark sector, it's not just one particle, it's a plethora of particles, and it kind of mimics our quarks and gluons, which we were talking about. So you have dark quarks, hypothetical dark quarks, and dark gluons, and they interact. So that's something we call dark quantum chromodynamics. It sounds very spooky,
yes,
but that's the kind of model we are looking at. Now, the interesting thing about that model is it gives stunning signatures in the detector, which we typically would not look at. So that's what my research is focused on, like looking at this science for dark QCD, which is super new. It's very exciting, and yeah, we haven't found it. I mean, again, if we found it, you would have known, but we have to look at everywhere, right?
Wow, that's amazing. So how do you know? You're looking for something so elusive. How do you actually know if you found something?
That's the $1 million question, right? Because typically we look for a small signal over large background. In our case, the background is the known standard model processes, and our signal would be like a handful of events indicating the presence of the new physics we are looking for, in this case, dark matter. That's where I think all this machine learning and things come in, because we are looking at a very complex data set. So we try to use machine learning to tell us like, where an anomalous event might look like. But we don't trust a machine learning algorithm all the way. So we'd also, if the algorithm says, look at these events more carefully, they look suspicious, then we'd go and try to see like why those events are suspicious. And maybe we'd see like, no, that actually indicates something new. So that's kind of how we look for new physics in our large data set.
That's really interesting. I feel like other communities, and this is my personal opinion, I feel like other communities have something to learn from the particle physics community because I feel like in my field, for example, new physics is not something you hear a lot. That term, that expression is not used a lot because, for example, like quantum mechanics is a very successful theory, and it's successful to the point where we're almost, rule out any sort of new physics, as it were, the possibility of new physics, or anyone trying to look for new physics is seen as, not wise, as it were. Whereas in the particle physics community, it's like the entire community is actively looking for new physics. And I feel if we did something similar to that in other fields, maybe we'd find more new physics, you know? But that's just a thought there that I had. Now, if we indeed found something new, what would it mean for the everyday man? Okay, first, what would it mean for our understanding of the universe if we finally understood dark matter, for example? Could it change our lives in any way, do you think?
That's very interesting because, of course, as we all believe, dark matter exists. We are going about our life without worrying about that in every day. Of course, if we know what dark matter is, that's going to expand our understanding of how universe works at a very basic level. And I think that would be like a victory of humankind in some sense. Like man landed on the moon, so that was a victory. Did it change our life? Maybe it did in terms of technological innovation.
Yes.
But the average person on the street, it hasn't really helped them. But I think it's just a victory of the human spirit that we can find something which is so hard. So in that sense, finding dark matter or any new physics, as you alluded to, is just going to increase our understanding of how the universe works. And even from like time of the Greeks and Romans, people have been invested in looking at this in whichever way they could. And we are kind of carrying on the tradition.
Yes, indeed. Wow. And who knows, you know, if somehow it's, you know, new physics gets developed, that might lead to new technologies, and you never know what that's going to mean for, you know, when it comes to applications for everyday life. Anyway, one last question before we call it a day today. As I said, you know, time flies on the show. For anyone, perhaps, you know, younger ones curious about physics or maybe wanting to get into science, what advice would you give? Is there a fun way they could start exploring topics like dark matter, for example, would you say?
Indeed. And I think our field, or any field in science, we need younger people to come into that. Otherwise, the field would die. So
exactly.
So my idea is keep your eyes open. I mean, when I was growing up, we didn't have internet. I only used email when I was applying for my PhD. Whereas nowadays, there's so much information. Keep yourself aware of that. That's going to tell you what's happening. I mean, listen to shows like Dr. Dada's. I mean, he's talking about new breakthroughs in science, and there are so many of them, so many articles. So keep abreast of them. Study hard. This is a cliche, but study hard because it's a tough competitive world out there. Keep your curiosity. That's, I think, the most important thing. I mean, be curious, be brave. Do not be afraid to explore career opportunities, which maybe not everyone around you is suggesting, because science can be very rewarding. I mean, both of us are scientists here, and we absolutely love what we do. So yeah, I would just say, like, keep an open mind, learn new things. Get all the information. You guys are so lucky nowadays. You have so much information around you. I wish I did when I was growing up.
Yeah, I'm the same. I'm the same. And yeah, with that, we'll try to conclude on today's show. It's been an absolute pleasure to have you with us on the show. We've learned a lot about dark matter, about what the state of knowledge is, and what we can look forward to in future, you know, and the sort of amazing engineering that goes into actually doing the research. And that's really, really enlightening for us and very engaging as well. Thank you so much. And so this brings us to the end of our show for today. Thank you, our listeners, for tuning in into this week's edition. Keep your radio dials locked to Jambo Radio Scotland. And until next time, everyone here at Jambo Radio, we would like to shout out to you and thank you for listening and say, stay curious.